Let us start. Today we are going to start this new chapter, DC motor. So here the syllabus includes
Excuse me, sir.
yes.
Sir, actually, what assignment you have given? Will you discuss or not?
No, assignment is your task.
Sir, actually, there is one doubt in question number 7.
Okay, you can ask me at the end of this class.
Okay, sir.
So first topic is review of EMF and torque equations. That means we are going to derive the EMF equation for DC generating mode of operation and torque equation for DC motor mode of operation. Okay. Then classification based on the field connection. Okay. Next is losses and efficiency, and to determine this efficiency we need to know these two tests, Swinburne's test and Hopkinson's test. And then is torque speed characteristics and speed control of DC shunt and series motors. Okay, so we will be seeing from this classification topic that there are different types of DC machines based on the field connections. So mainly there are two types. First is separately excited, then is series excited, and then this series excited are further classified into series connection, shunt connection and compound connection when both series and shunt fields are present. Okay, and out of these different types we will be considering here only shunt and series motors. Okay, so this chapter is basically on DC motors. Okay, but for that we will be requiring some uh, portion of DC generator like the EMF equation as well as the operating principle of DC generator. Okay, so here we are not discussing the construction of DC machine because it is not included in your syllabus, but you must know a little bit of it, so you go through it by yourself. I will be giving you a very brief idea. Okay, so DC machine is basically a rotating machine which can be used both in generating mode of operation as well as in motoring mode of operation. That means it is basically an electromechanical energy conversion device. Okay, so when electrical power is given to its armature winding, which is normally placed on the rotating part, that is the rotor of the machine, then at that moment we need to excite the field winding also to create the field poles, that means the magnetic flux. Normally electromagnets are used. If we use permanent magnets for smaller machines, then there will be no requirement for the excitation to the field winding. Actually there will be no field winding in case of if we use permanent magnets. Okay, but permanent magnets are used only for small machines. Okay, so here the machines, any DC machine will have two main parts. One is static part, that is known as the stator, and the rotating part, that is known as the rotor. On rotor the armature winding will be there. In case of generating mode of operation, the induced EMF will be induced in that conductors of armature winding, and the static part contains the field poles and field windings. Okay, so first of all we will derive the EMF equation. So this is based on generating mode of operation, but it will be requiring for motoring mode also. Okay, in case of motoring mode of operation we will call this EMF as back EMF. We will see later on. So first of all, this is a cross sectional view of a DC machine. which will be operating as a DC generator. Okay, so you can see this is the static part, okay, which is having some foundation or base fitted on the ground or some platform which is fixed. So this outer part is called the yoke, which is used to carry the flux produced by these field poles. So this is a 4-pole machine. We can see alternate north south poles are there. So this type of construction which is having alternate north south poles are called heteropolar structure. Okay, so this is one pole. This section is called pole shoe. This is called pole core. So on this pole core, these are the field windings. Okay, so when these field windings are excited by some DC voltage source, this portion will be magnetized, and some pole as per the direction of current or the windings in which they are wounded, based on that this will be either a north pole or a south pole. Okay, so if it is a north pole, then this will be south pole, and then again north pole, then again south pole. In this way alternate north south poles will be there, and this type of construction is called heteropolar structure. So when these field coils are excited, north south poles will be induced. That means flux will come out from north pole and it will enter, it will pass through this air gap and then enter the rotor, and then again enters the air gap, and then this will go in this way. Okay, and in this way also, and this will also go in this way. In this way, through this yoke, it will complete its path. Okay, so here this the situation is, first of all, this magnetic flux is created by exciting the field windings, and then by some prime mover this rotor is rotated. So what is this prime mover? Anyone having any idea?
So which collects the mechanical energy.
Yes, which supplies mechanical energy to this machine. Okay, so in practical situation, or suppose in a power station where alternators are used to generate electricity, so what will be the prime mover?
Motor.
Sorry,
Motor.
no, your power station, in power station, what will be the prime mover?
Turbine.
Yes, turbine. So based on the type of power station, the turbines are different types. If we suppose in case of thermal power station, normally these turbines are steam turbine. In case of hydro power station, normally these turbines are water turbine. Okay, so based on the type of power station, different types of turbines are used. Okay, so these turbines will supply the mechanical energy to this rotor. So that means now the situation is, this rotor which is carrying the armature winding is rotating under some magnetic flux. Okay, so here flux, suppose B, that is flux producing source, we can say, that is constant, or constant in magnitude as well as in space. Okay, and the conductors are moving. Okay, we know that to have or to induce some EMF in a conductor, we need some relative motion between the source of magnetic flux and the conductors. Either the source can move or the conductors can move, that is motional EMF. There is another type of EMF, that is called transformer EMF. In that case, both the source and the conductors, source means flux producing source, and the conductors in which the EMF will induce, both are stationary, but the flux, magnetic flux itself is time varying. Okay, so in that way we also can create some change in magnetic flux. So as per Faraday's law of electromagnetic induction, we need either a relative motion between the source, when the source itself is when the flux produced by the source itself is constant. In that case we need some relative motion, but if the flux is time varying, then both the source can be static. Okay, is it clear?
Yes, sir.
So in case of DC machine, the field or the flux producing source is on the stator, and the conductors in which the EMF is going to induce is on the rotor, which will rotate. So there is a relative motion. So this motion is created by some prime mover. So when this rotor is driven by this prime mover at some constant speed, then there will be some induced EMF in these conductors of the armature winding. Okay, so this is the situation. So here we are considering some DC generator or DC machine operating in generating mode of operation, whose field coils are already excited to create this magnetic flux density distribution along this air gap periphery. Okay, and this armature, which is nothing but a arrangement of some conductors. So that armature is driven by some prime mover. So the situation is some conductor and which is rotating under some magnetic flux. So there will be some induced EMF. So we need to derive the expression of that induced EMF. Okay, so let us assume the machine parameters. So let L be the rotor, length of the rotor. So this is actually the cross sectional view of the rotor. So actually the rotor is cylindrical in shape, so it must have some length. So these are the slots in which the conductors are placed. Okay, and this is the shaft. So this is cylindrical in shape, so it must have some length. So let us consider that length is L. Okay, so next D be the diameter of the rotor. This is already shown here. This is the diameter, and P be the number of poles. So in this case, in this diagram, 4 poles are shown. Actually in DC machine, the poles are poles will be in pairs. That means there will be always even number of poles, either 2 or 4 or 6 or 8, etc. Okay, so here in this diagram 4 poles are shown. So let us assume that in a machine which is having P number of poles, phi be the flux per pole. So see, this is not the total flux, this is flux per pole. That means flux produced by only one pole. Okay, and Z with the total number of conductors. That means in the armature, let us consider that there are total Z number of conductors. Actually there are different coils in the armature. So this is one type of coil which is known as lap winding, and this, if this is a single turn coil, so there are two sides. This is one side and this is one side. So this makes that this coil is having two conductors. Okay, so we are assuming that this machine is having Z number of conductors in total. Now A be the number of parallel paths. Now these coils are connected in different way for different kinds of machine. Okay, different kinds of machine means based on the application. In some cases we will be requiring a higher current carrying capability, or we may require a higher voltage across the output terminals, that is the brushes. Okay, So in this DC machine we are having another part which is known as the commutator. This commutator is nothing but a mechanical rectifier which rectifies the induced EMF. Here inside this armature AC voltage will be induced. So after passing through this commutator across the brass terminals, we will have DC voltage. So this mechanical rectifier is the commutator. Okay. Now in case of motoring mode of operation, we will be giving DC voltage that will be converted into AC by this commutator, and then it comes to the rotor. Okay. So commutator is nothing but a mechanical rectifier which rectifies DC to AC as well as AC to DC. In case of generator, it converts AC to DC. In case of motor, it converts DC to AC. Okay. So based on the application, we will be requiring either a higher current carrying capability or a higher voltage across the brass terminals. Okay. So based on that, there are different types of windings. So one is called lap winding, another is called wave winding. In case of wave winding, there will be fixed number of parallel paths, which is 2. Okay. So in this case, we are getting higher voltage across the terminals because more number of conductors are connected in series. Then we are having 2 parallel paths. But in case of lap winding, the number of parallel paths depends on the number of poles. If the machine is having higher number of poles, then the number of parallel paths will be higher. Suppose in a machine there are total 20 conductors. So if we connect these 20 conductors in 2 parallel paths, then each parallel path will be having 10 conductors, and suppose each conductor is producing 2 volt. So 10 into 2, that means 20 volt we will be getting across the brushes. 20 volt they are connected in parallel, so we will get across the output terminals 20 volt only. Okay. But if we connect these 20 conductors or a 4 pole machine in lap winding, then there will be 4 parallel paths. Each parallel path will be having 5 conductors, and these 5 conductors each will produce 10 volt. So 4 parallel paths each having 10 volt. So we will get, sorry, this is 10. So we will get the output voltage as 10 volt across the brass terminals. But you can see if the total current is 20 ampere here, so each path is carrying only 5 ampere. Okay. But in case of wave winding, there are 2 parallel paths only, so each path will carry 10 ampere, but that is not permitted because this conductor can carry only 5 ampere. So we have to reduce the total current value, that is 10 ampere only, to satisfy the current rating of the conductors. Okay. So that means if we require to increase the current capability, then we need to connect them in lap. If we need to increase the voltage across the output terminals, then we have to connect in wave. So based on that connection, there will be different number of parallel paths. If it is a wave winding, then the number of parallel paths is always 2, and if it is a lap winding, it depends on the number of poles. If it is a 4 pole machine, then there will be 4 parallel paths. If it is a 6 pole machine, then there will be 6 parallel paths. So that A is the number of parallel paths. Okay. So which is equal to P for lap winding, or which is equal to 2 for wave winding. Now we have to calculate the pole pitch. So what is this pole pitch? Pole pitch is defined as the peripheral distance between two similar points of two adjacent poles. So similar points means we can consider the center of the pole. So this distance is called pole pitch. Similarly, we can calculate this pole pitch from this point and this point, or from this point and this point, or whatever here it is shown from this two the central point of the magnetic zone. So from this point to this point, this is also two similar points between two adjacent poles. Okay, so here this north pole and this south pole are two adjacent poles, or this south pole and this north pole are two adjacent poles. So we have to consider two similar points of these two poles. Okay, so that peripheral distance is called the pole pitch. So how to calculate that pole pitch? We know the distance, this distance, that means that is d by 2, or we know this total distance, that is d. Okay, so we can calculate the periphery or the circumference of this inner circle, that is the cross section of this rotor. We can calculate this. So that is nothing but pi d, or 2 pi r, if d is equals to 2r. So in that case it will be 2 pi r, or this is pi d. So pi d, that is the total circumference of this cross section of this rotor, but only this section is under this pole, or this section is under south pole, which is same as that of pole pitch, which means if we divide this length by p, we will get pole pitch. So pole pitch is equal to pi d by p. Is it clear to everyone what is this pole pitch and how to calculate it?
Yes, sir.
Next, area under each pole. So here we are considering that this air gap length is very small, so this peripheral distance and this length are basically same. Okay, so area under each pole, what is it? We have to multiply this length into the length of the rotor, which is same as that of this length of this pole shoe. This section is called pole shoe. Okay, so length of this pole shoe and the length of this rotor, they are basically same. So if we multiply this pole pitch into the length of the rotor and the length of the rotor, then we will be getting the area under each pole. So pi d into area under each pole, into length of the rotor will be is equal to the area under each pole. That means this is the area through which flux is coming out from this north pole, or flux is entering to a south pole. Is it clear? Area under each pole, is it clear or not?
Yes, sir.
Okay, so now we have assumed that flux per pole is phi, so we can calculate the average flux density by dividing that flux by this pole area. So B average, that is the average flux density under each pole, so that is phi by per unit area, so that is pi d by p into L, that is the area under each pole, and after simplification we have p phi by pi dl. Okay, so this is the average flux density along the air gap periphery. Okay, and which is more or less uniform. Now how to calculate the induced EMF? We know the induced EMF is calculated using the Lentz's law, that is E equals to minus of n d phi dt. Okay, and the modified version of this formula is B L V. Okay, here the flux is constant, the variable is this velocity, that is the position of the conductor. So we are going to apply this BLV formula. Okay, So B average we have calculated, L we know the length of the rotor, V we have to define. So what is this V? V is the linear velocity of the rotor. Okay. So induced EMF in a single conductor. So here we are going to consider only one conductor. Okay. So induced EMF in a single conductor can be calculated using this formula, that is B average into L into V. And what is this V? V is linear velocity of conductor, which can be written as pi dn. How can we write this V equals to pi dn? Any idea? What is the relation between angular velocity and linear velocity?
Sir, V equals to R omega.
Yes, V equals to R omega. And what is this omega? Omega is angular velocity.
Angular velocity.
So R omega we can write 2 pi n. What is this n? N is the speed
Frequency.
in RPS.
Cycle. Yeah.
Cycles per second. Okay. So n is the speed in RPS, revolution per second. Now we can write pi into 2R into n. What is this 2R? Nothing but d.
Diameter.
So V equals to pi dn. We can write like this. Okay. So n is rotational speed in RPS, revolution per second. Now we have Z number of conductors in the machine, and we have calculated the induced EMF in a single conductor. So we will be able to calculate the total EMF across the brushes. Okay. There are Z number of conductors and there are P number of parallel paths. So how many conductors are there in a single path? Total conductors Z and P paths are there. So how many conductors are there in a single path? Obviously Z by P.
Z by P.
So this is the number of conductors in a single path, and so what will be the induced EMF appearing across each path? This into the induced EMF per conductor, that is we have calculated BLV. Okay. So this into BLV will give you the voltage appearing across each path, and those paths are connected in parallel. So we are having that much of voltage across the brushes. See, suppose the arrangements are like this. Suppose we are considering 4 parallel paths, and here the brushes, 2 brushes are placed, and the output terminals are like this. Okay. So each path is having Z by P number of conductors, and each conductor is producing BLV amount of induced EMF. So this into this will give you the total voltage appearing across these brushes. All paths are connected in parallel, so we will be getting the same voltage across these brushes. Okay. So here EA, that is the total voltage appearing across the brushes, that is EA equals to Z by A, B average into L into V. Now putting the expression of B average, that is P phi by pi dl, and after simplification we have this expression EA equals to Pn phi Z by A. So this is the expression of induced EMF in a DC machine. Now this is one of the form. There are other forms by which we can express this induced EMF. So if we multiply both the numerator and the denominator by 2 pi, then we will be having this expression. Now see, P, number of parallel paths, number of poles in a machine, that is constant for a given machine. Flux, that is flux per unit, flux per pole, that will vary depending on the field current we are providing. Z, that is total number of conductors, which is also constant for a given machine. A, that is also constant for a given machine. So Pz by 2 pi a, that is actually a constant, and 2 pi n, that is nothing but omega m, that is the mechanical angular velocity. So we can express like this: Pz by 2 pi a into phi omega m. Pz by 2 pi a is denoted by this symbol Ka, which is known as armature constant, and that is a constant for a given machine. Omega m is angular velocity in radian per second, which is equal to 2 pi n, where n equals to velocity in revolution per second, rotational speed or velocity in rps. Okay, so this is another way of expressing the induced EMF. Ea is equal to Ka phi omega m. There is another way of expressing this Ea. So these are three different ways. So we have seen this one and this one, and what is this? This we can derive from this expression. Here, if we convert this RPS into RPM, then we have to divide this capital N by 60. That means this small n is equal to capital N by 60. Okay, this is RPS, this is RPM. So if we divide RPM by 60, then we will be getting RPS. So here this small n can be replaced by capital N by 60, then we will be getting this expression. So all these three expressions are very important because they will be requiring for solving numerical problems. So any one of these three can be useful for solving any particular problem. Okay, any question up to this? No question. Okay. So next is a derivation of torque equation. So let us see. We are using, or we are considering the same machine, but here the situation is different. Okay. Here, first of all, here the field windings are excited by some voltage source, and then some voltage is applied across the armature terminals through brush commutator. Okay, so what is the situation now? Some current carrying conductor under the influence of some magnetic flux. Okay, so these conductors, these current carrying conductors will experience some force, and that force will give rise to this electromagnetic torque, and due to that torque this rotor will start rotating. Okay, in case of generator we were giving mechanical input through this rotor. That means some prime mover is used to drive this rotor, but here as we are giving electrical supply to the armature, the conductors will experience some force, because this situation is that some current carrying conductors are placed under some magnetic flux. So this current carrying conductor will experience some force. So initially when the rotor is not rotating, depending on the position of this conductor, all the conductors will experience some force, and that those forces will produce some couple, and that couple give rise to this electromagnetic torque. Okay, so here we can see, if we consider one conductor here and another conductor here, so these two conductors will produce some couple. Okay, so it will experience some force in this direction and it will experience some force in this direction, so they will produce some couple. Okay, so we have to derive that torque, the generated torque or developed torque in case of motoring mode of operation. So the machine parameters we have already assumed. So L will be the length of the rotor, D with the diameter, P with the number of poles, phi with the flux per pole, Z with the total number of conductors, and here the new parameter is that IA, that is the armature current. Okay, because in case of force calculation we will be using the formula BIL. Okay, for induced EMF calculation we have used E equals to BLV, but in force calculation we have to use this formula BIL. That is why this armature current is required, and again A with the number of parallel paths, which is equal to P for lap winding and which is equal to 2 for wave winding. Now again we have to calculate the pole pitch. So this is pole pitch, and then we have to calculate area under each pole, because we are going to calculate the flux density again, because the formula is BIL, so we need B. So here average flux density will be given by this expression, that is P phi by pi dl, same equation. Okay, so up to this it is similar to that of EMF derivation. Okay, now current through each conductor. See, suppose there are 4 parallel paths. So if the armature current is IA, what will be the current through each path? Obviously IA by 4, because if we apply KCL at this point, all the parallel paths are having equal number of conductors, that means they will have same resistance. So based on that, this current will get divided at this point equally. So each path will carry equal amount of current. So if there are 4 parallel paths, so I by 4 will be current through each path. So current through each path means each conductor, here all the conductors are connected in series in each path. So current through each path means current through each conductor. Okay, so here we have assumed P parallel paths. So current through each path is IA by A, sorry, A parallel paths. So current through each conductor is IA by A. So therefore force on a single conductor is B into IA by A into L. So that is the force, B average into IA by A into L. Up to this, any question? No question. Okay. So force on a single conductor is B average IA by A into L. Therefore torque on a single conductor. So when force is given, how to calculate torque? We know that if we consider one circular path, suppose this is one conductor which is experiencing force in this direction, and this is the distance from the axis of rotation and the point of action of the force. So if we multiply these two, then we will get the force. Okay, so here force is B average by IA into L, and this distance is nothing but D by 2, that is the radius of the rotor. So force is given by this expression into R, that is D by 2. So torque on a single conductor is given by this. Is it clear to everyone?
Yes, sir.
Now how many conductors are there? Z number of conductors are there. So total electromagnetic torque will be multiplied by this will be multiplied by Z. So this is total electromagnetic torque developed, TE. Now putting the values of B average, and after simplification we get that Pz by 2 pi a into phi Ia. Now Pz by 2 pi a, what is this?
K.
This is nothing but Ka,
Armature constant.
armature constant. But one problem is there, that is, though as per this expression, this is same as that of Ka, but this is not Ka. This is somewhat different from Ka. So what is this? This is actually Kt, which is called torque constant. So why we need to need two different symbols to represent these two? Because basically they are different. How they are different, I will say later on. Let us denote this as by the symbol Kt. Okay, so Te is equal to Kt dot phi into Ia, and here Kt is torque constant, which is Pz by 2 pi a, and that is same as that of Ka. But why we are representing this by the symbol Kt? Because see, in case of induced EMF equation, this is Ka phi omega m. So what is the dimension of Ka? Ea, that is voltage, divided by phi, that is Weber, omega m is radian per second. Okay, so volt per Weber per radian per second. Now see the dimension of Kt, that is torque Newton meter by Weber by ampere. Sorry, this by ampere. So dimension is Newton meter by Weber by ampere. So see, their expressions are same, which means their magnitude will be same, but their dimensions are different. That means they are having different units. So that is why we need two different symbols to denote them. But since their magnitudes are different, we can write this also. T is equal to K phi Ia, and sometimes we will be using this expression only. Okay, so Kt and Ka, they are not same, but their magnitudes are same. Their due to their dimension, since they are having different dimensions, so they are basically different. Is it clear? Anyone having any doubt? No. Okay. So let us find some relation between this EMF and developed torque equation. So from the induced EMF equation we have this, and from the developed torque equation we have this. So both K and Kt are having same magnitude, therefore we can write comparing these two equations, we can write Ea by Te is equal to K phi omega m by Kt phi Ia, which can be expressed as omega m by Ia, because K Kt will get cancelled out and phi will get cancelled out. Therefore we can write Ea into Ia is equal to omega m Te. So what is this Ea into Ia and what is this omega m into Te? Tell me.
Armature current or armature voltage.
So Ea into Ia, that is the product of voltage and current. What is it actually? Some power.
Power.
And omega m Te, what is this? they are related by some equal sign, so obviously this will be some power. This is also some power, isn't it? Omega mt, that is also some power.
Rotating
So
power converted to electrical power.
now what is what is the significance of these two powers? First of all, let us consider EAIA. In case of motoring mode of generating mode of operation, we are giving mechanical energy as input. So when we are giving some mechanical energy, there will be some mechanical opposition like friction between moving parts and some air resistance. So if we subtract those oppositions, that means some losses, then we will get some mechanical power, and that amount of power is the input to the machine, and which will be converted into electromagnetic power. Okay, so this is the electromagnetic power developed in case of generating mode of operation. Now consider motoring mode of operation. We are giving some electrical input to the machine. So when we are giving some electrical input, there will be some electrical losses like core losses in the core of the machine, ohmic losses or copper losses in the winding of the machine, and if we subtract those losses from the input, then we will be having some power which is input to the machine, and that amount of power is converted into mechanical power inside the machine. So that is again some electromagnetic power in mechanical form. So that amount of power is this omega m Te. So both of these are electromagnetic power. This is in electrical form, this is in mechanical form. Is it clear?
Yes, sir.
So equation 3 is the power balance equation. It shows that in case of a generator, the mechanical power supplied is equal to the electrical power developed in the armature, and in case of a motor, the electrical power supplied is equal to the mechanical power developed at the armature. Okay. Okay, that is all about this review of EMF and torque equation. So next is classification, but time is almost over. Okay, today up to this.
So there is a question 7.
Just a minute.